Hello, everyone. I am Yiwei Lyu. It's my pleasure to present our work on probabilistic safety assured adaptive merging control for autonomous vehicles. And this is a joint work with my colleague Wenhao Luo and my advisor, Dr. John Dolan. So talking about motivation, it is a fact that the autonomous vehicles will have to share roads with human drivers. So our goal here is to provide a safe control method to help the autonomous vehicles interact with human-driven cars safely and efficiently under uncertainty. The scenario we're going to study here is the rapid merging scenario, which is one of the most important and typical one, where the autonomous vehicles will interact with human-driven cars. So here's an illustration of the rapid merging scenario, where we have the green car on the main road as the ego vehicle and the red car on the ramp as the merging vehicle. So we assume this is a human-driven vehicle, and we're going to control this green car to for safe interaction. And the uniqueness about this scenario is that we have to balance the driving aggressiveness and the conservativeness at the same time. And we set the technical objectives for this paper as, firstly, we will have the safety as our priority as we seek formally provable safety guarantee for autonomous vehicle control. And secondly, we want to remove the finite support uncertainty assumption, which was made by some of the related works in this area. And thirdly, we want to provide solution feasibility guarantee for these optimization-based controllers. So first, let's take a look at some simple background of the control barrier function. So we start by defining an admissible control space. And we say that any controller that belongs to this space will render the safe state set H forward invariant. And in this work, we consider the pairwise vehicle safety. And here's how we define the safety set. We want the inter-vehicle distance larger than a predefined R-safe, which is a predefined parameter. We call it safety margin. And this is how we define our control space, that as long as we can find such kind of control that satisfy this kind of inequality, then we say this controller is safe. So for the method part, first we need to take a look at the system dynamics. In this work, we formulate the vehicles as double integrators, where X and V are the position and velocity of each vehicle. And U here is the control input, which is the acceleration of the ego vehicle. We include epsilon here as the random Gaussian variable to represent the motion uncertainty in this system. So here's our completed formulation as a bi-level optimization problem. So this is the objective function, which is a common optimization-based controller with a minimally invasive manner. So this UE here is the control input we are going to optimize, which is the acceleration of the ego vehicle. And U bar here is the nominal control. So the first constraint we have is the minimum and maximum allowed value for this UE, which is the kinematics constraint. And the second constraint we have is the safety constraint, where we formulate it as a chance constraint CBF control barrier function problem, with eta on the right-hand side as the assigned confidence level. And the last constraint we have is the feasibility constraint. So the alpha here represents the driving strategy, the driving aggressiveness or conservativeness, the driving style. So it is also a minimal invasive manner, the minimally deviation control from the nominal alpha bar. And from high-level understanding, it can be understood into two parts. So the first part, we want to optimize over the control input U to provide a probabilistic safety guarantee. And secondly, we want to optimize our driving strategy to provide solution feasibility guarantee. And you may wonder, how do we get the last constraint? So to understand that, we first need to figure out when does an optimization problem become infeasible. So here we reorganize our safety constraint into the such kind of form, AU less than or equal to B. So A term and B term are state-dependent variables. And with this safety constraint here and the kinematics constraint here, we can see that the solution infeasibility happens when the overlap of the two intervals becomes empty. And if we further derive this inequality, we can actually get an upper bound or lower bound for this control input U based on the sign of the A term. And as I said, A term and B term are just state-dependent variables. And through observations, we can see if we decrease the value of alpha and A term remains unchanged, we will get a decreased upper bound and an increased lower bound. While keeping that in mind, we're trying to visualize what it looks like. So here, in the case when A is positive, we have this red dashed lines from right to the left, representing the decreased upper bound. And we have the U min, U max here, which are the fixed value. And the resulting, the blue intervals are the corresponding reducing solution set, while alpha keeps decreasing. And we can see that the solution infeasibility will happen when this red dash line passes the U min. And the similar things happen here. So while the A term is negative, when we decrease the value of alpha, we will get an increased lower bound. And that means this red dash line will moving from left to the right and making this blue interval shrinking a bit further while we keep moving it. So this is our proposed algorithm. Since this is a stepwise optimization problem, at each step, we first optimize over control input U to provide the safety guarantee. And at the meantime, we work on the optimization of the alpha, which is the driving strategy for the next step through the forward kinematics to ensure the future feasibility. So now we come to the experiment part. So the goal is to show the proposed method valid and efficient. And here's our experiment setup, where we have the ego vehicle on the main road and merging vehicle on the ramp. And here we set the confidence level eta to be 99%. For the validity test, our objective is to demonstrate the probabilistic safety over a large number of trials. So we run the 400 trials and randomly generated the initial conditions of the ego vehicle, including the positions, velocity, and its driving strategy alpha. So here we have this black dash line as our R safe, the safety margin. So any trial that's on top of this black dash line means this trial is safe. And we can see among all 400 trials, we get a 0% completion rate. And the second test we want to show is the efficiency test, where our objective is to compare the performance of our proposed method with a traditional control barrier function with fixed parameter alpha. And for this test, we will have the initial conditions of the ego vehicle the same. And the only difference between the two controllers will be with or without the updated CBF parameter alpha. Okay, so now we have the blue line here as the traditional control barrier function with fixed alpha value. And this yellow line here is our method with updated alpha value. The green zone here represents the time interval where in our proposed method, the alpha value gets updated. And we can see that these two lines actually share the same performance before they enter the green zone. And they start to deviate since they enter the green zone. And for the traditional one, without updating the alpha, it soon becomes infeasible and further breaks the safety margin. And that's how we show that our method provides a dynamic solution feasibility guarantee in runtime. And for the second part of the experiment, we would like to discuss what are the factors of the ego vehicle behavior generation. So the first one is, of course, the choice of parameter alpha. As we said, alpha represents the degree of driving conservativeness and aggressiveness. So here we want to play with different value of alpha and observe the merging outcomes. So here we are looking at the case where the ego vehicle is merging in the back of the merging vehicle. And we can see that the larger alpha is, the more aggressive the driving strategy, is. And when we look at the case when the ego vehicle merges in front of the merging vehicle, we see that the smaller alpha is, the more conservative the driving strategy will be. And the second factor we would like to discuss is the initial conditions. So here is our testing scenario where we have two merging vehicles on the ramp, and we have the merging point here, and the difference between the two, demo 1 and demo 2, will be the initial conditions of the ego vehicle. So in case 1, we will give it a closer initial location from the merging point here and a faster speed. And in demo 2, we'll drag it a bit further from the merging point and give it a slower speed. And we want to see if we use the same strategy, what will it be like? So here's a case 1 demo where we in this case we can see that the aggressive driving strategy actually makes the ego vehicle merges in between the two merging vehicle, but the conservative one makes it merges in. The aggressive merging strategy makes the ego vehicle merges in front of the yellow car, but the conservative one makes it merge in between the two vehicles. And we want to see if we keep this strategy the same, what will happen if we drag it, originally it's here, but now we want to drag it a bit further and see what's happening. And now we see that this time the aggressive one makes it merge in between the two vehicles, but the conservative one makes it merge after the second vehicle. So from here we can see that by changing the initial conditions of the ego vehicle, we can also change the, while keeping the same strategy, we can also get the different results. So in conclusion, in this work, we proposed a bi-level optimization-based control framework to enable the autonomous vehicles to achieve consistent, safe, and merging behavior under uncertainty, and with formally provable safety guarantee and solution feasibility guarantee in runtime. We also discussed the factors that affecting the vehicle's behavior generation. With that, I would like to conclude here, and thank you for the listening.
Thank you very much for the presentation, Yiwei, and I think that was great. Any questions? Okay, so I just want to I want to ask about what do you think about if there's a constraint to be satisfied as regarding let's say merging rules, road rules about merging, and those, say in some countries you have a merging rule where maybe the vehicle on the main lane has to go first before the other vehicle goes. So if there are this kind of rules as a form of constraint to be satisfied, I feel, would there ever be a need for, to bother about safety, and will the proposed how will the study basically change in the presence of this kind of a constraint? Just wondering.
Could you repeat what kind of constraint you're talking about?
A constraint, perhaps, let's assume like a road rule. A constraint like a form of a road rule, that the road rule is that vehicle on a particular lane must go in first in emergency situation before the other vehicle coming in. So if there's such maybe a road rule, maybe I take it to be a constraint perhaps in this context. So how will that affect the whole process, or the whole your research? I don't know if it affects your process in any way, basically. I don't know.
Yeah, that's a good question. So I think for this kind of extra constraints regarding the rules, we can maybe try to formulate as multi-layer. Once we decide to abide such kind of rules, we can choose the corresponding appropriate alpha value, or so given the initial conditions like this, and okay, we can change the alpha value to manipulate the outcome like whether we want to merge in the front or merge in the back. Does that make sense?
Yeah, thanks. Yeah, thank you very much.